All right, so we're going to talk about IR spectroscopy now, and we're going to give a textbook explanation of IR spectroscopy. So first of all, molecular bonds can vibrate by stretching or bending in a number of ways. All right, so the one that we're going to be most interested in this semester is stretching, because that's where we can get the most information, but it turns out there's lots of ways. Remember that these things sort of act like springs. So this is going to be like scissoring, these guys going back and forth, and there's different kinds of vibrations. All right, but again, it's the stretching that we're going to be most interested in. So the energy necessary to cause vibrations to change are different for different kinds of bonds, right? So you might have a large energy gap for this state of a frequency of a CH bond to this state, right? And remember that E is equal to H nu, right? So a big gap is going to require a big frequency in order to get a transition from this energy state to that energy state, and a smaller one is going to require a lower frequency. So the IR spectrophotometer irradiates a sample with all frequencies of IR light, and it's the frequencies that are absorbed that tell us what kinds of bonds are present, which we've said before. The couple facts here, which are not going to be a big deal for us, but just a couple ways that these are done is that they're oftentimes done with a salt plate. We've got one in the lab. I think it's got a crystal plate, but there are other ways to that these samples are prepared and analyzed. All right, but let's look at a spectrum. So this is cool, isn't it? Because this is very much like what we saw in a previous conversation. The infrared absorption spectrum plots the amount of transmittance. I didn't make much about this in the previous conversation. The percent transmittance is here, and the wave number is here, okay? And everything below the 1500, I alluded to this in a previous conversation, is called the fingerprint region, and we really can't get much information out of that. It's called the fingerprint region because if under the exact same conditions, two different groups analyze the same compound, then they're going to get the same fingerprint. But for the most part, that's not what we're doing. We're mostly going to be looking above 1500, and we're going to be looking for some telltale peaks. Were you part of a previous conversation with me? Do you remember what I said that was? Amazing. It's very prominent, and everybody cares about it, right? It's this bond right here. It's the OH bond at 3400 or 33 something. Okay? So the percent transmittance is over here, the wave numbers down here, and these wave numbers, we're going to get used to those. So what is wave number? Well, wave number is actually frequency divided by the speed of light, and that's why we call it reciprocal centimeters, okay? Again, I don't think we're never going to be doing any of this math, so it's not a big deal, but it's a decent question, and so the frequency, you can actually tell what kind of energy is being absorbed if you know what wave numbers actually stand for. Okay, and then finally, a signal on the IR spectrum has three important characteristics. We're not going to get very deep into this, but it is wave number, which is the big one for us, and intensity and shape. We're going to get our eyes used to that. I said in a previous conversation that OH is going to give us big, deep, and wide, right? And so deep and wide is what those things stand for. But really, it's the wave number that we're going to derive the most value from in our analyses of infrared spectra.